thanks to you guys, everybody, for showing up. This has been fun. Thanks for coming. But we're really gifted to have a guy like Tom as a member at our chapter. He has presented before, but that was early on with James Webb. He is with the Space Science Institute, and he works closely with James Webb, with Hubble, with the next one coming along. You're going to see stuff that you will see nowhere else.
Well, that's actually true.
Tom?
So 4 times the distance to the moon, 1 million miles away, in the cold and the dark. You can't see the red. Maybe you can.
The red dot.
The red arrow.
This is James Webb. Humanity has eyes in the dark.
Wow.
There's 4 cameras, 2 of which are also, actually 3 of which are also spectrometers. And I'm going to talk a little bit about spectrometers because that's how we actually tell, that's how you actually do science. The images are pretty, but the spectroscopy tells you what's really going on. And I called this early science, even though we're 2.5 years in to what was nominally a 5-year mission. Because the last estimate I saw for how long James Webb will last is 390 months. The requirement was 5 years, the goal was 10. We're going to get a lot more. We're going to get a lot out of James Webb, but this is what we've done so far. So, originally I was going to put a bunch of math in. You can all thank Melissa for leaving most of the math out. But there's two numbers you need to pay attention to. One is H naught. That's this term right here, H naught. That's the Hubble constant. I worked for the Hubble Space Telescope for, I don't know, 20 years before I started on Webb. Melissa keeps pointing out that she spent longer on Webb than I did.
20 years.
The other is that R. R is redshift. Redshift is a measure of how far away you are from something because as time continues, the universe expands. And as it expands, it's actually space-time that's expanding, so the light coming from things shifts further and further to the red. The telescope is a time machine. You're not seeing me as I am right now. Ernie's seeing me as I was 9 nanoseconds ago. You can look at it. If you look at the sun, you're not seeing the sun as it is right now. You're seeing the sun as it was 8 minutes ago. The nearest star is 4.3 years ago. And we can see all the way back, almost to the beginning of time. We do that with spectroscopy, and if you look at those little, the little red and blue points there, you can see that as you go back in time, they get more and more red. And the way we find those is with spectroscopy. So in addition to taking the pretty pictures, we take a different kind of measurement where we measure what the distribution of light is in different frequencies. So you guys all know about frequencies. You tune different frequencies on the radio. We tune different frequencies of light, visible and infrared. And we do it with this extremely cool little tiny machine. And these really are very tiny. Those little boxes in the upper left corner, they're about 1/5 of an inch wide and a little less than 1/2 an inch long. And there's 250,000 of them on NearSpec. And we can open them individually. We can open each of those little shutters individually. And then we put a dispersing element in front of it. And we get spectra. And we can take multiple spectra across different targets, many of them at a time. We can take 30 or 40 of them at a time out of that 250,000. That's probably who are these people having a party? What kind of a place is this? And you get the spectra look like that. So you have this you have basically an image of dispersed light. And that big dip on the far left there, it's what's called the Lyman alpha break. It's a particular ionization of hydrogen that tells you that it's very sharp and it's very nice because it makes it very easy to figure out how redshifted the target is. And some of the things that we have seen very recently, I should mention that every week I give a briefing to the mission operations team about the current state of the optical telescope, how our performance has been for the last week. I'm one of 7 or 8 presenters for the team. The first presenter every week is from the mission science team. Jane Rigby leads science for JWST. And she presented this result a few weeks ago, which is we've seen the most distant galaxy we've ever seen, and one of the most distant we'll ever see. This is from less than 300 million years after the universe started. And we know what it is because of where that Lyman alpha break is. And so there's 2 little galaxies there, and you can see the little arrow that points to the really distant one. Less than 300 million years after the universe turned on. When you look at that spectra, the other thing that you would notice if you were paying attention is that there's not a lot going on down in this part of the spectrum. That's because there's very few other elements there. When the universe was created, all there was hydrogen and helium and a tiny little bit of lithium. Everything else, all of the elements, everything that's familiar to you, was made in stars. And in this galaxy, the stars you're seeing are the very first stars. There's nothing else there yet because these stars hadn't had time to make it yet. So these are the very first stars in the very first galaxies at the very beginning of the universe. In a sense, James Webb has already accomplished its principal mission. We've seen the beginning. And everything else is just filling in the details. Yes?
How do you know?
So that turns out to be a great question.
That's a good question.
And it's very hard to answer. But we know that the universe had a beginning. We know that from the cosmic microwave background, which is a completely different way of measuring the universe. And we know that the universe had to start about 13.8 billion years ago, just under 14 billion years ago. Because you can see from the expansion of everything that came after, you can just draw a line back through that to where the singularity was, to where everything began. And you can see that this galaxy is from that period, from that spectrum down there, because of where that Lyman alpha break is.
Thank you.
So with that as a base point, if you select others that are newer, that's where you're going to see that as everything's moving forward.
If you look at these, everything is newer than this. That Lyman alpha break occurs later. The scale's actually flipped for reasons that are annoying. But the scale of where these things are is flipped. And so as a result, you know that everything since then, everything else we've seen is newer than this guy right here. So this is a pair of galaxies. There's a galaxy that's fairly close by, that's in blue. And there's another galaxy behind it in red. And the red one is the older one, and it's not a circle. It doesn't really look like that. Instead, what's going on is what's called gravitational lensing. There's nobody behind Kevin, so I can't use my standard joke. If Steve's head is a very massive object, then Steve's head would bend the light coming from Melissa. And you would see multiple images of Melissa behind Steve. But his head would have to be very massive. It's not that big. It's wonderful. So what's happening here is the light from the red galaxy is getting bent around that blue galaxy. And because it's spot on, dead center, it looks like a ring around it. It's called an Einstein. Usually they're not so neat and easy to look at. Instead what you get is these weird kind of strange bent things. And in this case what you see here is actually three images. There's this one here, there's that one there, and there's another one up there of the same background galaxy. And in two of those images, two of the three images, there's this supernova. This is a star that's exploded. It's the most energetic thing we see. So supernova are not all that rare. They happen when big stars reach a critical mass and their core collapses and they go off and they blow off their atmosphere in this enormous release of energy. The light from these two images has taken different paths as it's been bent around the galaxy in the foreground. So again, if I line up just right with Steve, I'll see multiple images of Melissa at slightly different times because he's not perfectly aligned. And so in 2035, this explosion will appear again up in that galaxy, not that one, in the top one. I should have brought a laser pointer. There'll be a third image of that same supernova in another dozen years, 11 or 12 years from now. And the exact timing of that will tell us a whole lot about the mass that's in between us and that galaxy. And the good news is it's extremely likely that Webb will still be around to see it, which is not what we expected.
So how do you know it's the same?
Spectroscopy. You take a spectral image, you get spectrum of that supernova, and then you can match up each of the individual lines in that spectrum. Gravitational lensing makes things very complicated to look at. So the galaxy on the right is all distorted. It looks very strange. It doesn't look like a nice, neat spiral galaxy because the foreground mass has distorted it. It's not nice and compact like Steve's head. But if you can map the mass in between, then you can put it back together and you end up with a nice, pretty picture like that. So we can tell that that is indeed a nice, pretty spiral galaxy that's been distorted by the mass in between. There are lots of these. We take pictures of deep fields. This is good zoom, James. This is James. We take pictures and we find all of these distorted galaxies, and we can kind of put them back together. And you can see the two different ways they get distorted. They get these loops around them when there's a mass that's almost directly in front. But when the mass is off to one side, you get that long, straight thing up at the top there, where you're basically seeing multiple images reversed of the same galaxy spread out over the sky. When you come in a little closer, the galaxies become a lot more regular. The left side is a composite of a whole bunch of different types of galaxies, a whole bunch of different structures of galaxies. On the right, you can see an example of that really is a spiral galaxy. The lower right part is a Hubble image. The upper left part is a Webb image. Webb sees further into the infrared. And so you see are these bubbles that have bright stars in the middle, and then star-forming regions around those bubbles. So the one on the left is a super nice spiral galaxy with a supermassive black hole in the middle. And so the core of the galaxy is very intense. There's a whole lot of star formation, a whole lot of energy in the center.
Is that a Webb picture?
So the left two are Webb images.
Okay.
The right one is a Hubble image
Right.
at the same scale. And I put the Webb image in there because the middle one and the right one are the same galaxy.
Oh wow.
But you can see they look completely different in the infrared and in the visual. It's just a function of if we see through all of the dust in the infrared, and all of the ultraviolet light gets cut out in the infrared. One of the guys on my team is a specialist in barred spiral galaxies, and this is an example of a barred spiral. It looks like there's sort of a gap in the middle with maybe a couple of spokes connecting the arms, the spiral arms, into the middle. And what's really happened is this galaxy has interacted with something else. And the gravitational wave from the merger of probably two galaxies, maybe more than two, has sort of traveled out along those arms and disrupted the spiral. And so now the spiral's on the outside, and it'll continue to get further and further out. And then it'll reform and do more interesting things. This is an example of, again, Hubble looking through the edge of a galaxy. On the left is the Hubble image, where you see a very large dust lane along the edge of this galaxy. On the right is the Webb image, where we see through the dust into the core of the galaxy. And then you get these very irregular things. And this is another one where two or three galaxies have interacted. And as a result, it's kind of torn the thing apart, and it's in the process of reforming. And so you have a supermassive black hole in the middle that's probably the result of a merger of multiple supermassive black holes.
Hey, Tom, can you go back to the previous slide? Each of those little red dots, what would you describe those as?
So these are clusters of stars. So they're not single stars, they're clusters of stars. Stars kind of get grouped together based on how they form in the arm.
Okay.
They get little bubbles in star forming regions.
Would you call those each their own
In each
little
of those-
solar system?
No, they're much, much larger than that.
Yeah, they're light years apart.
Yeah, they're tens of light years apart.
Wow.
So when you see a blob like that, that could be 100 light years or 1,000 light years apart,
That's right.
just within the blob.
Just within the block, yes.
That's a lot.
So you can see.
They could be nurseries.
That's awesome.
It's beyond.
Sorry, guys.
They could be nurseries.
Yes, stellar, they're called stellar nurseries. You get areas, especially as stars get to the end of their life, there's a few things that can happen to them. They can supernova, they can nova, they can blow up into big red giants. All of that material gets blown off into the interstellar medium, and then it recollapses again over enormous time spans, billions of years. And they reform, and you get new stellar formation. And that, again, blows out the areas in between these big blobs.
So would there be whole solar systems within, potentially around each of those stars? Or?
Yes. And in fact, I'll get to that as we get closer. Right when I came to the Institute, just the same year I arrived, in the Large Magellanic Cloud, we had a supernova 1987A, before Hubble was launched. And yet, the first discovery that Hubble made was what was the progenitor star for supernova 1987A. It turns out it was a blue giant that we found on the photographic plates taken from the ground that we were digitizing in order to make the Hubble Guide Star Catalog. And we've been watching this supernova ever since. We go back to it every few years. And this is the first time we've been back to it with Webb. And what we discovered is, if you look at that sort of blue teal colored thing on the left, that's the environment around a neutron star. Okay. The core collapse was not large enough to generate a black hole from the supernova. but it did generate a neutron star, which is basically degenerate matter. All of the matter at the core got squeezed into neutrons right in the middle, and it's spinning like crazy. And there are radio jets that are coming out from that neutron star, and they are generating ionized argon. The argon itself was made in the star and blown off in the initial explosion. The ionization is because of the radio waves that are being emitted from that rapidly spinning neutron star. And we can confirm that there's really a neutron star there because of this ionized argon. And again, that's spectroscopy, right? You don't get that from the image. What you get from the images, there's definitely something compact in the middle of that cloud around the supernova. Spectroscopy tells you what it is. Usually I have to say something about what a polycyclic aromatic hydrocarbon is, but this crowd knows about polycyclic aromatic hydrocarbons. This is a cloud around a star that's blown off its outer atmosphere several times. And in the process of doing that, it's created this big cloud of polycyclic aromatic hydrocarbons that are now re-radiating ionized light, re-radiating light from the ionization of those clouds. This is how complex organic molecules get made in space, by generation of ionizing radiation onto carbons and hydrogens and oxygens in deep space. So this is the other way to make polycyclic aromatic hydrocarbons.
It'll be a Tesla.
Once you're done flying and have used up all your polycyclic aromatic hydrocarbons, you may be interested in ethanol. These are ethanol clouds around a star. They're created through a similar mechanism. Again, the ionizing radiation from the star interacts with the medium around, more carbon-rich medium around the star. And what we find is this spectrum of ethanol. And so ethanol plus some methylation, so there's some methane, there's some other alls in there. I don't know if this would taste good. But there's plenty of alcohol in there. The other thing we do is chromatography. And this is some work that was done by my colleague Marshall Perrin, who is, he's the actual wavefront scientist. I'm an assistant wavefront scientist. I used to have the coolest title. I was assistant wavefront operations scientist and principal computer science scientist for the telescope team. Now I am trending guy. Marshall is still the wavefront scientist. I don't know why that's fair. But Marshall's a chromatography expert. And so the way a coronagraph works is, if you want to see Melissa, what you do is you put an opaque thing in front of Steve, so that you can look past Steve and see the much more interesting thing behind him. The way a coronagraph works is we put a occulting thing over the star, and we can see the disk behind it. We can see all of the material around it. And in this case, there's a debris disk, and there's a secondary debris disk, and then there's that white thing up there that's kind of out of the plane. That wasn't there 5 years ago. When we looked at it with Hubble, you didn't see that. Now, the first thought was, well, maybe Hubble wasn't sensitive to it. It turns out it was. If it had been there, Hubble would have seen it, but it didn't. Instead, something else is going on, and what Marshall thinks is going on is there are two debris disks. They are interacting, and something in the secondary debris disk, probably a Jupiter-sized planet, is grabbing material from the primary debris disk and throwing it up out of the plane. So it's as if Jupiter was coming along and grabbing up comets and asteroids and flipping them up out of the plane of the solar system. So this is a solar system around Fomalhaut.
When you say that wasn't there 5 years ago, in reality, the event that you're seeing
Yes.
is thousands of years.
Hundreds of thousands of years ago, yes. Yes, good point.
So it was there.
More than 8 nanoseconds ago.
It's observation 5 years.
Yes, but the Hubble observations 5 years ago did not show that thing that they're, astronomers are not very creative. They're calling that a cat's tail because it looks like a cat's tail.
Really? I don't know.
I'm
seeing a butterfly.
That's what's making that change.
So this Jupiter-sized, maybe super Jovian-sized planet is moving around, is lifting things out of the plane of the solar system.
It's gravitational.
Yeah,
Gravitational pull,
it pulls
yeah.
it out of the secondary disk and
Yeah.
kicks it out. All right, more spectrum. There's this giant planet. It's about twice the size of Earth, and the question was, it's very hot. It's a very hot super Earth, and there's a question of there are two things it could be. It could be that it's just a lava planet, that there's no atmosphere around it, and the other possibility is that it has an atmosphere that's being replenished from this lava ocean. And so what you do is you make a model. So the red model is if it's just a lava planet, you'll get a spectrum that looks like that. And if it's a lava planet that also has an atmosphere around it, you'll get something that's closer to the blue. And the purple crosses are what you get when you actually look with NearCam by looking at through different filters, and MIRI using the medium resolution spectrometer. And so what we know is that while this is a lava planet, it's very hot, it's not very hospitable, even though it's in the same range, the same size range as Earth. It's not going to work out well for people who are like us. But it definitely has an atmosphere. All of those little purple dots, all the little error bars, or the crosses are the error bars around them. Definitely favor the model that says there's some kind of atmosphere there.
Would that be comparable to Venus?
It's a lot worse than Venus. Venus does have a solid surface, even though it's very hot. Mercury even has a solid surface. This is worse than Mercury. This is really awful.
We should go there.
Not many of them.
We should go there.
We should go there.
Oh yeah, this is another one. When Jane told us about this one, I didn't believe it. And I got Mike McElwain to explain it further to me. If you look at the this is a planet that's got an atmosphere. It's a normal sort of gas giant atmosphere. But when you look at the spectrum, what you discover is that it doesn't have a nice smooth spectrum like the little yellow lines would show. Instead, there's this peak in silicon dioxide. So if you went to this place, you would need a really good filter because basically silicon dioxide is quartz. This thing has tiny quartz particles in its atmosphere. It would be like walking through a sea of quartz. It would be very uncomfortable.
Yeah.
But again, spectroscopy. But back to imaging. This is two images of Uranus. Uranus has a very cool ring system. There's 11 different rings there. And we've recovered all of them, though it took 2 separate observations to get them all. No other telescope around or on Earth can get this level of resolution and this level of dynamic range. This is something that's unique to Webb, and we can do it every day. In order to do this, you need something like Voyager or New Horizons, but we can do this every day. So, some of you may have seen the aurora. I didn't because the weather sucked.
Yeah. Same.
We had previously seen aurora on Jupiter. They're very cool. What we have never seen is aurora on Neptune, and they've looked repeatedly. They looked with Voyager, they looked with New Horizons, they looked repeatedly and extensively for aurora on Neptune. Webb can see aurora on Neptune. We can see ionized hydrogen at multiple latitudes. This is the first time that anyone's ever detected ionized hydrogen at Neptune, and it's the first time that we've seen the aurora of Neptune. This is just a very cool picture. This This is Saturn. You can see the individual rings. You can see the Cassini division. There was a bunch of spectroscopy done on this to try and figure out exactly why the rings have different brightness. There are two theories. One is it's just a different level of density among the rings. The other is that maybe there are different kinds of ice. You can get a couple different kinds of ice. You have ordinary experience with that. You can get an ice cube. An ice cube is amorphous ice. You can get snow, which is crystalline ice. The spectra of those two things are slightly different. And so by taking spectra of each of the individual rings, you can say maybe those inner ones are amorphous ice and the outer ones are crystalline ice, or vice versa. They took spectra of each of the rings around Saturn. They are all highly crystalline ice. So the differences in brightness have nothing to do with different kinds of ice. They have to do with different densities and different temperatures of the ice around Saturn. So this is extremely pure. We now understand that it's even more pure than we thought it was. And it's all crystalline ice. It's all snow.
Cool.
It's water ice?
It's all water ice. Oh, that's a good point. Another possible explanation was carbon dioxide ice. Do I have a thing about that? I think I have a thing about that. Yes, I have a thing about that. About carbon dioxide versus water ice.
Oh my gosh. Cool pictures. Beautiful.
I could say.
I love Jupiter. Jupiter's an interesting problem.
Pictures. It's beautiful.
Jupiter has this giant storm.
Yeah. Right there.
From when Galileo first spotted it up to today, there has been this permanent hurricane, the Great Red Spot. The Great Red Spot is shrinking. It will go away, probably in my lifetime, certainly in my daughter's lifetime. Another 30 to 40 years and it will be gone. And so a feature that has been there for all of the time that humanity has been looking at Jupiter will be gone. But in the meantime, you can do a really good look at individual weather patterns at different latitudes on Jupiter. There are all of these different interactions of jet streams at the different latitudes that produce these very turbulent zones, which again, you guys already know about this. You get a wind shear, it's really ugly. So the interaction between these counter-rotating bands has produced some really interesting interactions between the various latitudes. And that shear is what's destroying the Great Red Spot. It's eroding it away. And it won't be there much longer. We live in a privileged time.
What is the type surface of Jupiter?
So Jupiter's a gas giant. What you see is mostly methane.
Okay.
There's ammonia further down,
Right.
and then there's carbon further down. And when you get all the way to the bottom, at the core of Jupiter, is a giant crystalline carbon diamond.
Okay.
If only you could recover it. All right, so comets come in different shapes and sizes. This is a main belt comet. Comets like Halley are distant comets. They come in from way the hell out. The main belt comets orbit much, much closer. They all come in past the orbit of Jupiter and then back out a little ways, but they don't go way out into the Oort cloud. Webb was able to get a really good look at this one comet, which is 283P Reed. Again, astronomers are really good at naming things. And we took a bunch of images and took a bunch of spectra because we wanted to know what are main belt comets made of. Are they made of water ice or are they made of carbon dioxide ice? Both are likely to happen. But what's this particular comet made of? Well, if you look at a couple of different comets, Hartley has enough going on that you can see both water and you can actually see there's a trace that could be ammonia and lots of carbon dioxide ice. This comet, 238P Reed, has a bump in the water and nowhere else. There's no carbon dioxide in this comet. So this is the ultimate snowball. Again, it's just pure water ice, no carbon dioxide ice at all. The closest thing that Webb can look at reliably is Mars. We've only done it once in 2022. It's actually not true. We did it again in 2023 for a director's discretionary program, but the science team hasn't told us what they found yet. This is the last thing that we've actually seen science on. And, you know, Mars is pretty well studied. There's not a lot to learn, but the fact that we can do temperature and brightness and recover the Martian atmosphere composition from spectra tells you a lot about the capabilities of Webb. So that's about the closest thing you can see with Webb. Except, and this is the part where it gets interesting. Oops. Okay, so one of the cool things about Webb is it doesn't have a tube. The primary mirror is out there in the open. This is the part where you have to turn off the recording. You don't have to, you don't have to turn it off, just don't show the screen. Okay, so I'm going to show you something that's unpublished. So please don't put it on social media. It's not a secret, but most journals won't accept stuff that's been published somewhere else. So Webb's primary gets hit with meteorites all the time. The ones that are big enough to affect the performance of the telescope, called the ones that affect the wavefront. There have been 67 impacts that have been big enough that they leave these little divots, and they look like little bow ties. And this is called a pill image, a pupil imaging image. And so it's a picture of the primary mirror itself. And they leave these little things that look like little bullseyes. And we only take pictures every couple of days to try and detect what's going on with changes in the wavefront. And I asked my colleagues, isn't there some way we can figure out what's going on? Can we see changes in the point spread function? And so they started looking through the data, and what they found is every once in a while we get flashes. These flashes are very short. So what we do is we take a bunch of images. We take very short images and we stack them up. We combine them together so that we get more dynamic range by making multiple images of the same target. And what happened is, so here's in less than 10 seconds, you get this flash that's bright enough to fill the whole field, and then it's gone. So in a 20-second period, you get this one very bright flash. And when you're done, if you look up there where it says C5, there's a little divot. There's a new little feature on the face of the observatory. What we believe is going on is we're catching the flash from something striking the primary mirror. And when that happens, whatever hits us gets heated up. And it makes this very bright flash, very close. It's out of focus because it's right on the primary, it's not the focal. And what we'd like to do is figure out what it is. Again, that's spectroscopy. So it could be lunar regolith. We know that little bits of the moon have been blown off by meteorite impacts. And some of them may end up at L2, which is out there 1 million miles away, 4 times the distance to the moon. It could be little bits of comet that have gotten ejected off as these main belt comets that come sweeping through the inner solar system. Or it could be something else entirely. And we'd like to find out what that is. And this particular observation was taken while we were doing spectroscopy with another instrument. So if we knew how bright this flash was, we should be able to recover one frame of spectroscopy to find out what it was made of. The problem is, this is on the guider. This is the guide star. The guider's not even a science instrument. It's just this thing that we use to point the telescope. And as a result, this detector has never been photometrically calibrated. So we don't know how bright that flash is. And so that's what we're doing right now, is trying to figure out just how bright that flash is. So that's the cool thing that my team is doing right now. Well, not today, but they'll get started again on that.
with these little meteorites that hit the Webb, how does that affect the space station? I mean, there's going to be the space. How does that affect the space station? It's up there? Yeah, because it's affecting the Webb.
So they do the same sort of thing that we do, which is if you look at the backside, we have lots of coverage. So most of the observatory is protected by the sun shield, which is this 5-layer thing that's multi-layers of kapton. And so when something hits the sun shield, it might penetrate the first layer, but it never gets through the second layer. On the back side of the observatory, there's multiple layers. Anything that hits that first layer is going to vaporize in the first layer. Space station does the same thing, only they have more layers and thicker layers, because they have to deal with larger things. They have to deal with things like bolts.
Because their altitude is higher.
Well, no, their altitude is much lower. They're
Oh,
only,
it is? Okay.
Yeah, they're only at, anybody know? You know, 180 miles? And space station's much lower. Even Hubble is in the 300, well, it used to be 10. I think it's down like 306 now. They're in a very low Earth orbit. We're out in an environment where there really shouldn't be very much. The problem with the low Earth orbit is people have been putting crap into
Space
these
junk, yeah.
into orbit for decades. And so they have literally, I mean, they've been hit by paint flecks that leave a hole this big.
Solid junk.
The holes that we're leaving are this big. And the things that we're getting hit with are tiny. They're smaller than grains of sand. They're just little tiny things. And yet, even so, I mean, you can see that, you know, we have an allocation for how much obscuration. So the main effect of this, of having these little divots, is obscuration. We lose part of the reflective surface of the primary. So don't tell anybody about the flashes. So even after 2.5 years, I keep coming back to this. This is the fine phasing 3, and you can we can go back to show you. This is where we first focused the observatory.
First focus what?
The observatory, and discovered that our specification was 131 nanometers. In this image, we're at 67. So we are twice as good as we were required. But that's not the great part. The great part is in the background. All these little dots in the background are galaxies. This isn't even an exhaustive search. This is just the brightest 288 things my boss found in the background. It's not a star.
Wow.
Webb is better than it was supposed to be, and it's going to last longer than it was supposed to be by a factor of at least 3, maybe 6. And as a result, it's going to be working a lot longer than I am. So that's Webb. And I think this is the last time I'm going to talk about it. The next time I do a talk, I want to talk about this.
Sorry, before you continue on this, I want to ask a very naive question.
Sure.
But in all the space study that you guys are doing, any signs of other life, UFOs?
Oh.
You know, I know maybe that's not, you know, but
No,
I'm just curious.
So the question, is there life out there? Is a really good one.
Right.
And so I got 2 answers. One is we don't know.
Okay.
Right now we know of one place in the universe where there's life.
Okay.
You're standing on it.
Right. So all these other stories about sightings and things like that. So basically,
So I would say
the radars.
all of the stuff you've seen about sightings on Earth, the evidence is extremely weak.
Okay.
And it's very difficult to reproduce.
Okay.
And it's very difficult to predict from.
Okay.
The fact that there are polycyclic aromatic hydrocarbons in the universe is an indication that complex organic molecules exist. And, you know, complex organic molecules stand up and walk around sometimes. It's silly talks.
And do we know yet if we could live elsewhere, like somewhere? Is there another?
Right now, there is nowhere else in the universe that will support human life
Okay.
other than this one right
Okay.
here.
You see, honey, I'm not from Mars. Okay, thank you.
the third rock from the sun.
So,
Number three.
you use very interesting language to talk about how long the universe has been here, and I cannot remember the words you used. But you said 14 billion years. What was here before that?
Before that.
What do the scientists think was here before the universe?
So there's a couple of problems with even asking the question. Because if time is an element of space-time, and what you're seeing is expanding space-time around you, and when you turn the clock back, as it were, what you get at the singularity is there was nothing. Now, that's one option, right? That the universe came into existence from some process. 13.8 plus or minus 600 million years ago. Once you get to that point, we have no useful information. Now, Penrose and Mather both believe, and I used to tell people I've met 6 Nobel Prize winners, no 7, but one of them hasn't won it yet, but Adam did win. So I've met 7 Nobel Prize winners, they all have a different answer to that question. Mather thinks that the universe, as we think about it, that space-time as we think about it, has always been there. It's not down to time, but that whatever happened to the singularity, the quantum fluctuation that created the space part of space-time, filled an empty universe. Penrose thinks there are multiple universes and that each of them evolved in a different way. Adam says it doesn't matter because there's nothing that you can see beyond that event, and so you can't say anything rational about what happened before 14 billion years. So I mean that's a hard question to even understand.
Thank you for answering.
Yeah.
So a couple of questions. One is, what's the best estimate of how many galaxies are out there?
So my flip answer is billions and billions.
Yeah.
So I'll say
Doug, I would say n plus 1.
Yeah, it's ever expanding universe. Forever.
So there's billions of stars in a typical galaxy.
so it's billions and
Billions and
times
billions.
billions.
Yeah.
N plus 1, right.
N
All
plus
those opportunities.
For life.
Yeah. Oh. This goes back to this goes back to is there life elsewhere in the universe?
Can't be.
So one thing is it easy to make life? It would be really helpful if we had one more example. The problem with only having one data point is you can draw any line you want. If we had just one more data point, doesn't have to be little green men in their spacesuits. If we just had one other example of life anywhere in the universe, that would be very helpful. We don't have that yet. The mission that Melissa's working on is going to look for more habitable planets using this very large field survey model mission. She works on the Nancy Grace Roman Space Telescope. I want nothing to do with Roman for lots of reasons. But it uses an imager that's much larger than Hubble or Webb. And it stares at chunks of the sky for a long time so that you get some more population statistics about planets, about potentially habitable planets. And it's got this instrument that's not really, that's a technology demonstrator really, that will let you get spectra of some of those targets. The most promising ones, you put a spectrograph, you put a coronagraph with a spectrograph on it. That will go a long way. But the real answer is a much larger telescope, much more expensive, your tax dollars are worth, called Habitable Worlds. Habitable Worlds is leveraging the lessons of James Webb, one of which is put a tube around your telescope so it doesn't get hit by micrometeorites. To improve our view of things in the middle distance, of things in our galaxy and in nearby galaxies, to improve the spectroscopy. I mean, that's the big thing, right? Both in the infrared, but also in the ultraviolet. Webb can't do ultraviolet at all. We're purely infrared telescope because the goal of Webb was to go back and look at the dawn of time, at the very beginning of the universe. And we've done that, and we'll continue to do stuff there. HAB worlds will let you directly image, not just infer, but directly image worlds and directly get spectra of individual planets to find out if there are signatures of life. One thing I left out because it's another pure spectral thing, there's no pretty picture that's associated with this, the detection of dimethyl sulfide. We thought there was a detection of dimethyl sulfide around a planet, but it was very ambiguous. And now people think that we didn't detect it because the detection threshold is below what Webb can really sense. We would need a much longer integration and a much better positioning of the occulter than you can actually get with the Webb observations we have. Habitable worlds with a larger mirror and a more sensitive spectrograph would be able to definitely do that. So we can't quite get there, but the next mission might. And if we getting one more data point would go a long way toward telling us whether life is extremely rare and we're the only instance, or is extremely common. If I had to bet, I don't know what I do because I don't have any data to work from. I have only this one data point. Anything else? Yeah.
What can we look forward to regarding our galaxy?
So I think you will see more. What we'll do is more looking for exoplanets. The coronagraph people are really starting to hit their stride. They're really understanding how the various coronagraphs are calibrated now, and so you'll see a lot more coronagraphics and coronagraphic spectroscopy with Miriam, and so you'll see. I think you'll see a lot more exoplanet work. I don't think I'm supposed to say what's in cycle 3 yet, so I don't think that'll be public until Monday. But if you ask me on Tuesday, I'll tell you more about exoplanet cartography with James Webb. Yeah.
It seems to me, we talk about going to Mars, and I'm thinking, why? What's until we figure out how to travel at light speed, are we not wasting our time?
No, I don't think so. So the thing about Mars is a challenge. The biggest challenge with Mars is radiation. But if you can figure out what to do about that, and there are some obvious options, right? The big one is carry a whole lot of water. For that, you need a very large spaceship. I can think of one. They could probably carry a whole lot of water. But once you get there, or once you get situated so that you can deal with the radiation problem, there are a whole lot of resources on Mars, such that you could make your own fuel, you could make your own oxygen, you could probably figure out with a couple of iterations how to make your own food.
But why?
Well, it lets you look at another environment, right? So the single biggest problem in the world today, well, maybe the second biggest, is global climate change. We have only closely studied one global climate. The TAPS paper that basically freaked everybody out about nuclear war was based on one dust storm at Mars. If we could get a better understanding of how climate and weather behave on Mars, that would help us explain how climate and weather behave on Earth, and it would give us an environment we could experiment with without endangering all of humanity. I should point out that's way outside my area. I can tell you about OTE trending all day long, but that's what I think about it. All right, thank you.
Thank you, Tom.